problem. It's a picture of a function, and we want to interpret a lot of information and be able to explain where that information is coming from. Those are all qualities that I think are very important in mathematics: communication, graphing, and understanding what's going on without numbers. Okay, so number 14, we have this funky-looking function that is defined on the interval from 0 to 9. And so this function starts at the origin, drops down, has a local minimum at x is equal to 1, crosses the x-axis at x equal to 2, has a local maximum at x equal to 3, crosses the x-axis again at x equals 4, has a local minimum at x equals 5, crosses the x-axis again at x equals 6, and then has a local maximum at x equals 7, a local minimum at x equals 8, but that one never crosses the x-axis, and then stops over here at x equals 9. Okay, so this is the graph that we're given, and what is especially important about this graph is that this is the graph of f prime of x. And we are trying to answer some questions about the original function f based on our graph of f prime. Okay, so our first question asks, on what intervals is f increasing? And then it says to explain. Okay. So I look back over here at this function, and I want to constantly remind myself that this is a picture of f prime, not a picture of f. So looking at where f prime is increasing and decreasing will not answer my question over there, which is where is f increasing or decreasing. So looking back over here at f prime, I would like to know where f is increasing. So when f is increasing, what is true about f prime? Okay, so when f is increasing, so this is my thought on this, f is increasing when f prime is positive. Another way of saying that, or you could say, or f is increasing when f prime is above the x-axis. Okay, so my connection is that f is increasing when f prime is positive. So over here, when I look at this graph here, f prime is positive from 2 to 4, and then also from 6 to 9.
I was also going to say that we know wherever it's 0, that's going to be a flat spot on our f.
Okay, so I'm going to ask you to say that one more time without the word it.
Okay, I'm sorry. Where the function of f prime hits 0 on the x-axis is going to be a flat spot on f of x.
Good. Okay. So did you guys all hear what she said? Okay. Great. So these are really good observations to make. And so, and with that in mind, I wasn't trying to pick on you, Jennifer, but from now until the end of question number 14, the word it may not be used. in any way, shape, or form. It is a 4-letter word. Okay, so on question A, on what intervals is f increasing? F is increasing on the interval from 2 to 4 and from 6 to 9, and our reason is because f is increasing when f prime is positive, or equivalently, f is increasing when f prime is above the x-axis. So the goal of the explanation is to link the characteristic of the graph of f prime with the property that we're looking for on f. Okay, so our next question here, part B. Part B is at what values of x? At what values of x does f have a local maximum or local minimum? Okay, so I like Jennifer's observation about when, and I'm going to write this over here, when f prime touches the x-axis, f is flat. So how do we know when we have a local maximum on f? What is happening on f itself? F is going from going uphill to downhill at a local maximum. So what is that telling us about f prime?
Going from above the x-axis to below.
Yeah, so when f goes from increasing to decreasing, f prime is going from positive to negative, or from above the x-axis to below the x-axis. So f has a local maximum when f changes from increasing to decreasing. Good question. So should this be f or f prime? F is changing from increasing to decreasing. F prime changes from positive to negative. Or equivalently, f prime changes from above the x-axis to below the x-axis. So f prime changes from above the x-axis to below the x-axis. Okay, so our reasoning is f has a local maximum when f prime changes from above to below the x-axis. So when I'm reading from left to right, we're always reading left to right here. When f prime changes from above to below the x-axis, that only occurs right here and x is equal to 4. So f has a local max at x is equal to 4. Okay, so how about the local minimum? The local minimum, well, a local minimum is going to occur. F has a local minimum when f changes from, well, f is going from downhill and then switching to going uphill at a local minimum. So f changes from decreasing to increasing. So in terms of our f prime graph, that's telling us that f prime changes So if f is decreasing, f prime is negative. So f prime changes from negative to positive. And so f has a local minimum our f prime is reading left to right, going from below the x-axis to above the x-axis, and that occurs in two places. That occurs at x equals 2 and x equals 6. All right, so when you're looking for, when we're looking at these explanations, then we're looking for both an answer of what are the x values, and then a connection back to the graph. And so our connection is that f prime changes from negative to positive when f has a local minimum. The thought process in between, at least for me, is when I'm reading the graph, I imagine in my head, okay, local minimum looks like the bottom of a bowl. So what's happening on my function? My function is going from downhill to uphill, decreasing to increasing. So f prime, what happens there? F prime changes from negative to positive. Okay. So there's a lot of links in between there, but the final connection is f prime changes from negative to positive. F has a local minimum at those values. All right, any questions or comments about that? Okay. All right, so that was part B. Part C, on what intervals is f concave up or concave down? When is f concave up and concave down? All right, so we talked about the second derivative last time, and our connection with the original function f and concavity had to do with the second derivative. And so when f is concave up, that corresponded to our second derivative being positive. And when f is concave down, that corresponds to f double prime being negative. The problem with these connections is that it completely ignores our f prime graph over here, which is what we have to work with and where our justification needs to come from. And so we need that third link in this triangle here. When f double prime is positive, what does that tell us about f prime? So f double prime is the derivative of f prime. All right, so think about it for a second. If f double prime is positive, what does that tell us about f prime? Think about it for a minute, and then say hi to your neighbor, and discuss it with your neighbor.
No clue.
Because I mean, it's still the same. It's just another derivative going like that. This prime is.
Wait, I'm trying
But
to.
now we're going f prime is still it's the same rules still apply. So
Yeah,
f the x-axis.
which we have. Double prime
Yeah.
double prime. Positive.
And in your discussion with your neighbor, avoid the word it altogether. If your neighbor says the word it, take away their candy.
This is something we do for f double prime.
Where it's just turning.
Oh, okay.
Well, that's when f prime is positive. But when we say that it's positive, f prime is positive, we're saying that the slope
Doesn't double prime work more?
Okay, so did anybody come to a consensus with your neighbor about what should happen with f prime?
Maybe. Maybe I'm like.
Any ideas? Anybody come up with any ideas? Okay, increasing? So you're saying when f double prime is positive, f prime is increasing. Why does that make sense?
That's what you told us to write down.
Okay, so other than what you wrote down last time, why is that correct? I mean, yes, we can memorize it, but why is this link a valid link?
Well, why would it be negative? I mean, if you're increasing, you're still going to continue to be positive when you take the derivative.
Okay, so when this function f prime is increasing, then its derivative should be positive, and its derivative happens to be f double prime. So this link between these two is just like the link between f is increasing connects to f prime being positive. It's the same link. We're just now talking about the relationship with f prime and f double prime versus f and its derivative. So this link is really the same link. We're just one level shifting that up. Okay, so this tells us, since f is concave up when f double prime is positive, and f double prime is positive when f prime is increasing, that means that we can finish out this triangle since these are all connected to each other. So if we look at f prime, and I look at where f prime is increasing, that's going to tell me where my original function is concave up. So f is concave up when f prime is increasing. And so that tells me in this case, these are the intervals where f is concave up are, well, let's see, they're the intervals where f prime is increasing, so that's from 1 to 3. And then from 5 up to 7. And then from 8 to 9. Okay, so these are the intervals when our original function f is concave up. Now we have the same connection over here. F double prime is negative. Well, f double prime is the derivative of f prime. So when f prime is decreasing, then our second derivative is negative. And so we can connect that back to our original function f by looking at where f prime is decreasing. So f is concave down when f prime is decreasing. And so our intervals where f is concave down are the intervals where f prime is decreasing. So from 3 to 5. And from 7 to 8.
What about 0 to 1?
And 0 to 1. I totally forgot about 0 to 1. So don't forget about 0 to 1. That goes in there too. Thank you. And from 0 to 1. Okay. So again, on these explanations here, I'm having trouble with that word today, but on these explanations, we want to talk about, okay, f being the function we're interested in is concave up, or in the case over there, concave down, and we want to relate that back to the characteristic of the graph that we're looking at. In this case, we're looking at the graph of f prime, so we want to be able to describe what characteristic of this graph is telling us that f is concave up. And the characteristic is that f prime is increasing. Okay, any questions about that? Okay, so the very last question on number 14 is question D. And D is asking about points of inflection. F has inflection points or points of inflection at what x values?
2, 4, and 6.
Okay, and so you're going with 2, 4, and 6. So I would say that 2, 4, and 6 are places where f prime is equal to 0. And in fact, those are places where f prime changes from negative to positive. So that means that my f function is going downhill and then coming uphill. So that this here is a local minimum. So the places you described are local extrema. Okay, so but points of inflection are sort of like local extrema at a different derivative level. Points of inflection are places where concavity changes. And so concavity on f prime is, so f is concave up when f prime is increasing, f is concave down when f prime is decreasing. So points of inflection are places where concavity changes, and that occurs when f prime changes from increasing to decreasing or decreasing to increasing. So in other words, local extrema of f prime are inflection points on f. Okay. So f has points of inflection. I'm going to shorten that to POI. When f changes from concave up to concave down, or vice versa. And how does that relate to f prime? Well, f changes from concave up to concave down, or vice versa, when f prime changes from increasing to decreasing, or vice versa. So when f prime goes from going uphill to going downhill, or going from downhill to going uphill, another way to say that is i.e. when f prime has local extrema. And those local extrema occur at the tops of hills and bottoms of valleys on f prime. So we have 1, 3, 5, 7, and 8. X is equal to 1, 3, 5, 7, and 8. Okay. So I think it's really important to take some time to think about questions like 14 and like 13, because these questions hopefully will help you to sort out the connections between f prime, and f double prime. And in my opinion, it takes a while to process those ideas. So there are no new practice problems over this weekend. I want to encourage you to continue to work on the 4.3 practice problems. In particular, these graphical types. So I'd given you sort of 2 lists of practice problems last time. And the first list involved 11, 13, 14, 15, 17, and 21.